Kia ora koutou katoa, now mai haere mai. My name is Michael Kingsley and I'm the Interim Dean of Science here at Waipapa Taumaturau, the University of Auckland. It's my pleasure to welcome you all to this inaugural lecture of Professor Stephane Coen, a physicist whose work explores the extraordinary behaviour of light and whose journey to this stage is as fascinating as the science that he studies. Stephane grew up in Brussels and earned his PhD in non-linear optics before arriving in Auckland for what was meant to be a short postdoc. That short stay turned into a long and impactful career when he returned to join the university as a lecturer in 2003. Stephane has made major contributions to our understanding of non-linear resonators, optical frequency combs, and the phenomenon of spontaneous symmetry breaking of optic fields. His current research pushes the boundaries even further, developing an optical icing machine, a new kind of analog computer that uses light to solve complex problems. It's cutting-edge science with real-world potential. Tonight, Stephane will take us through his journey of exploring light, including a personal story shaped by passion, serendipity, and a not-so-subtle connection to the Lord of the Rings. Please join me in welcoming Professor Stephane Coen to the stage. Enjoy tonight.
So, kia ora everyone, and thank you for the kind introduction. When you hear this kind of words, you might think I'm somebody very special and that I had all these, I don't know how you put it, but you're going to think the story that the reality is much simpler, and a lot of it is not just about me, really. It's a lot of people who helped me along the way, and maybe also some luck that was involved. So we'll go through that in some details tonight. So we'll start from the beginning, and as Odile mentioned, I'm originally from Brussels in Belgium, and I grew up there, and you can see a number of pictures here. And so Belgium is the land of beer, chocolate, fries, and waffles. And yes, I do eat my fries with mayonnaise, as you can see it here. And also I have a brother. You can see him in the picture, older brother, who lives in Quebec, so he couldn't be here tonight. So I thought I would start the lecture talking a little bit about my family, because you might think that my family influenced my career, maybe, and the fact that I became an academic. I'll let you judge on that. So I'll start with my parents. My mom and dad, they are both doctors in paleontology, and so that means that holidays often look like that, looking for shells and whatnot in rock face that don't look so interesting. Apart from that, their own family is actually very different. And if I start with my dad's side of the family, he was actually the first one at university. None of his parents or grandparents or whatever did any sort of studies. For example, my grandfather was there. He started as selling shoes, and he became, he sort of grew up in the business, became a keen businessman. Eventually, finished director of a factory for the Bata shoemaker. You may have heard about that brand. It's not quite much around these days, but it's still in some countries. And obviously, when I grew up, I wore a lot of Bata shoes. And in that side of the family, we find also, seamstress, gardener, cooks, and you can see several generations of them. So absolutely no academic background until my father. And by the way, I'm the one on the left here. This is my brother. So on mom's side of the family, things are a little bit more different. These are my grandparents. They had 5 children together, and this is my mom here, 1946. And for first things, my grandmother had actually a physics degree, and this is something I actually learned quite late. And on that, well, guess what? He was a university professor. So that's my great-grandfather. He was a professor at ULB, the Université Libre de Bruxelles, where I later would make my studies. Now, moving on to my granddad on the left there. He's also a professor. He's a professor of physiology at the Université Catholique de Louvain. And in fact, it made it all the way to Dean of Faculty of Medicine, and did some role as some sort of DVC at some point, Deputy Vice Chancellor. Another person I'd like to mention is the brother of my grandfather, who we call Uncle Roger. And guess what? He's also a university professor, PhD in history and theology. He's the guy on the left, by the way, not the guy in red. He wrote several books around his career, and perhaps the most famous one you have never heard about, or actually participated in that one, is the so-called Grand Dictionary of Ecclesiastical History and Geography. And so work on that dictionary started in 1912. My Uncle Roger took over as editor-in-chief in 1960, which is kind of half a century later. And at the time, the dictionary was at letter D. And Uncle Roger worked on it for 49 years. He retired in 2009 when he was 95 years old. So he was a hard worker. And at that time, the dictionary was at letter L. Apparently, J took a lot of time because of all the Johns. And so this is still ongoing, and it's probably another century until this is finished. So my grandfather and his brother, okay, the last person I'm going to mention in the family is their uncle, which is my great-grand-uncle, and another university professor, you got it. He was an Egyptologist, and in Belgium, he was the one who set up the Museum of Egyptology in Belgium, and he was quite famous. And when the tomb of Tutankhamun was discovered in 1922, the Queen of Belgium, Queen Elizabeth, who was she had a passion for Egyptology, she naturally asked my great-great-uncle to serve as a sort of private guide to Egypt, and you can see them in a sort of good company there. Now, my great-great-uncle was sufficiently famous that, I don't know if you know, but Belgium is famous for their comic strips. And so this great-great-uncle actually inspired two different comic strip characters. And so the first one is Dr. Gross-Grabenstein in this comic strip of Blake and Mortimer. I don't know if it's well known in this side of the world. But you probably know the other one, is Professor Bergamote or Tarragon in Tintin and the Seven Moles of Crystal. So if that's not a sign of being famous in Belgium, I really don't know what is. So that's my family. You can draw any conclusion you want on how this impacted me, but here you go. So we'll move on to me. And so just to correct a little bit what our dean just said, I actually did an engineering degree. I didn't start with physics, but my specialty in engineering was physics. And that sort of a degree was set up in Belgium in the 1950s to serve the nuclear power industry that was in fashion at the time, then went a little bit out of fashion by the time I got there. It's back in fashion. But it was out of fashion by the time I got there, and so the degree was more geared towards optics and telecom and so on. And so this is a 5-year degree, and then I had to do a final year project, and this is only the beginning of the internet there. And so these projects were advertised on the wall, in the corridor, all the projects were lining up, and this is the page corresponding to mine. And so you would go there and read and, okay, pick them up that look interesting, pick one up that looked interesting, and this is pretty much how I got in this, okay. Yeah, that looks fun. I'd like to do this, please. And they selected me. This is my supervisor and co-supervisor. And the first thing I knew is that we had to go to Limoges, which is in the center of France, to pick up some equipment. And my supervisor, he was a young dad at the time. He had a 2-month-old baby. We went with his car. I was sitting with the baby at the back. And something I didn't quite realize, that Limoges is like 8 hours drive from Brussels. And all I had for lunch was an apple. And I was pretty shy. I didn't want to eat my supervisor and his wife's picnic, so I just ate my apples. But I survived the trip, and I also discovered that in Limoges they have a lot of duck breast and these sort of things. So that was good, and from there on I could actually start to work on my experiment. All these cartoons, by the way, are made by my supervisor when I presented my PhD. So what did I work on? So this is sort of I mentioned optical fiber rings in the title, and the sort of complicated version is nonlinear optics in current-driven passive optical fiber resonators. And so basically this is what this is about. Okay, we take an optical fiber, we make a ring, and we close the loop with what we call a bead splitter. So it's an element that lets the light go through in and out. It's basically acts like a partially reflecting mirror. Okay. So you might think this is something very simple. In practice, in reality, it's a little bit more complicated once you start to add a little bit of equipment around to make it work. But we'll keep things simple. And so I just would like to mention some important feature that makes this system a bit more complicated than what it looks. And the first one is that it has feedback, okay? Whatever happens during the light, during the round trip, it's sort of fed back into the system for the next round trip. And that's quite an important behavior. And so because of that, we observe the so-called resonance, okay? So what happened is that when the light that's circulating overlaps exactly in phase with the light that's coming in, well, you get more power in the optical fiber ring, and you get these peaks, and otherwise not. And we can go through that by stretching the fiber with piezo, and this is exactly what we have done here. And in fact, when I went to Limoges, we aligned the setup for the first time. We saw these things, and my supervisor looked at them and said, "Oh, the resonance looks great. You know, what do you think?" And I look at this image on the scope, and I had absolutely no idea what this was about. You know. But okay, I grew up from there a little bit. Now, the next thing there is in this system is so-called non-linearity, which is part of the title. And just to keep things simple, it's the fact that in silica, which is what optical fiber are made of, the speed of light slightly depends on the intensity of the light. Okay? Basically, when the light gets more intense, it actually slows down. And the result of that is that if you think about the way we access this resonance by changing the fiber length, well, if I'm trying to approach the resonance, the power goes up, and then the speed of the light changes. And this is a bit like we are changing the length again. Okay? And so two things can happen. You know, it could be that the resonance is rushing towards you, and you barely see it, and then we get sort of a low power levels. Or you are kind of chasing the resonance, running away from you, but eventually you can climb all the way to the top, and you get a high power level. And so we see this kind of hysteresis behavior. The system basically has some memory. It remembers which way you are doing things. Okay? And you can use that as an optical memory. You can actually store bits of information in that, all optically as bits of light. Okay? Now, this image may look a little bit funky, especially for our younger students in the audience. You have to keep in mind that this is the 90s. This was made on this analog oscilloscope, so it's literally an electron beam that hits some phosphor to get the image. And this is a Polaroid photograph of the screen, okay? And then I scanned it, so it's a long way to here. So another thing that was interesting in the system that's illustrated on this graph, you know, which our mathematically inclined people may recognize. It's a graphical way to find the intersection between a function on a graph. This is a green curve there, and the line, the yellow line here, which is at 45 degrees. Okay, and it goes like that. You start from some value nearby. You calculate the value of the function. You project it on the yellow line, and you repeat that. You can see we are approaching this point of intersection there. And in some sense, you know, this is what this system is doing. Okay, we start from some light field there. That's our x there. Something happened to it along the way. That's the function. And then we take the output from the fiber and feed it back as the input, and that's my projection, and then we do it again. Okay? And so it's exactly what happens. Now, nature is always a little bit more complicated than you think, and if you scratch the surface of that problem, you may soon discover that there might be functions in which this doesn't work. Okay? You're sort of going round and round in circle, and you never actually get to the intersection. And this behavior is called a period doubling instability because the system oscillates between two values instead of getting to the middle there. And this is something I studied as well, and you can see a picture of that. Just to give a bit of context, we had 3 pulses of light going around in the resonator, so we used pulses just to get higher power than instead of continuous light. And there was 3 pulses, and so they are grouped by 3. You can see it's oscillate between 2 states there, and this is so-called period doubling. And this thing can actually happen several times. Okay, from doubling you get to quadrupling. There's 4 states here. And eventually things get chaotic. This system actually displays quite a complicated chaos, and some people have envisioned to use that to do cryptography and whatnot. Now, interestingly, in the middle of the chaotic region, the system gets stable again for a brief instant of time, and it ends up into a period 3 behavior, where you oscillate between 3 states. And then that period 3 state can itself undergoes doubling, and here we have a period 6 behavior. Okay? So that's the sort of thing I was studying. Last thing I want to mention about my PhD, and which is going to be important for the rest of the talk as well, is this idea of the modulation instability. Okay? And just to understand that, we can look at this picture on the left, where you see a lens, you know, and you know what lens is doing. It focuses the light. Okay? The reason why a lens focuses the light is that there is more glass in the middle of the lens than on the edge. Okay? And what actually happens is that it takes more time for light to traverse the central part of the lens than the lateral part of the lens. Now, one way of adjusting the time is to have that shape of glass, but you can also adjust the time of travel of the light by playing with the speed of light. Okay? And when your speed of light depends on intensity, basically a more intense part of the beam will take more time to travel. And you get this exact phenomenon, but a long time, okay? And so when you take a uniform beam of light, an intensity that doesn't vary with time, well, it's never perfectly uniform. There's always noise. There's always a little bit up and down. Well, the ups are going to get focused by this process. We call that self-focusing, okay, or time length, if you like. And the result is that you start with a beam that is perfectly homogeneous, and spontaneously it becomes strongly modulated. And I call that my zebra state, okay, because it's sort of it hints to, or it has some connection to the patterns that we found on some animal like zebras. Something interesting about that is that you can see that this modulation is very fast. Okay, you can see the scale here. We are talking about picosecond. Picosecond is a millionth of a second. So this process allows you to create these very, very fast modulation without having just essentially spontaneously. Okay. And now another thing we can do with that signal, again, it's going to be important later on, is to look at the spectrum. We basically send the light into a prism and we separate the colors. And this is what it looks like for this case. And we see these characteristics side bands, okay? And you have to realize that we start with a single color laser, so essentially the central band, and the other bands emerge through that process. And so just keep in mind that picture for later on. We'll come back to it. So that was my PhD. And then at the end of my PhD, I went into a postdoc, and I came to New Zealand. And so a valid question is, why New Zealand? And it all has to do with these pictures here. We have to sort of go back a little bit to 1980. I was 7 years old. I was in year 2. This is me there next to the teacher. And my mom had that habit of always taking me to the hairdresser just before the photo shoot. So that's why I have short hair there. Anyway, in year 2, when you were 7 in Belgium, you had to do a speech in class at some point during the year. You might think it's a bit early, but these were the days. And so I really didn't know what to talk about. And my dad suggested, well, what about you talk about the Australian animals? That sounds exotic. Yeah, sure. And so there was no internet at the time, so what do you do? As a 7-year-old, of course, I went to the library, read some books, wrote a summary, organized it very well, right? No, it didn't quite happen like that. My mom did all that, and I just read I read the text in class. Okay? But I remember about Australian animals. Okay? Now, fast forward to my PhD, 1997-ish or whatever. And I was talking about koalas with my dad, and then I mentioned, koalas are marsupial. I remember that. They have a pouch. I remember that from that talk. And then my dad challenged me on that, and no, they're not marsupial. You're wrong. Okay, if you're right, I'll pay you the trip. That's what he said. Right? And of course, I was wrong. I was right. And he paid me the trip, except there was an Australian postdoc in our group there, and he said, yeah, don't go to Australia, go to New Zealand. It's much easier for some holidays. So that's where I went in 1998, and I had a great time. I did lots of stupid things that you can see here. This is about 100 meter high down to the river there. And so when a postdoc offer came in New Zealand, I sort of jumped at the occasion and came down here. And so here I am in New Zealand, and I met Professor John Harvey, who essentially hired me, and Leo as well, who is somewhere in the audience, I believe. Here we go. And at the time, so this was 2000, there was these new types of optical fiber that came along, and these are called photonic crystal optical fiber. And the reason is the name, and these fibers are sort of special because instead of being just plain silica, they are made of there is a series of air holes, very, very tiny air holes. You can look at the scale here, this is 10 micron. And these air holes run along the entire length of fiber, potentially over meters or hundreds of meters. And the result of that is that the light is forced to stay in this little hexagon in the middle, which is very, very tiny. And so you have so much light intensity there that these nonlinear effects I've been mentioning about, they get really, really strong. Okay? And so that was interesting. And John, through his networking, managed to get all these fiber. Leo set up a student to do the experiment using these very old, it was less old at the time, I suppose, but it was still already old. It's a krypton laser, red krypton laser. And I'm gonna run a little bit of a demo here because we're in a physics lecture, so I'll turn this on and I'll comment on it in a second. Anyway, because of this very high nonlinearity, when you launch laser light into these, the result can be quite dramatic, and you can sort of see that on the screen there. I'll dim the light. Obviously, this is a cheap version of that, which is made with a much more expensive laser, but you can see here, we are generating all these colors here, red, orange, yellow, green, and so on. All of that starting from a purely green laser that you can still you can see glowing there. Okay, So essentially, there's so much nonlinearity that light change color, and you can potentially generate white light, okay? And this is literally white laser light, okay? You don't, and this is called super continuum generation. It's a name that comes from the 60s, and it's come from the fact that we have a continuous spectrum. And you can see that my spectrum there is not quite continuous because that's a cheap version, okay? But still, we're generating, if you check the laser at the end, you know, this is a green laser, there's no green at the input, and yet we have like orange, yellow, and blue, and red at the output. So white laser light, why is that important? Well, what I did actually, so Leo had the student doing the experiment, so I did the modeling, and this is some figure from these modeling, which I did with Professor John Dudley, who is actually a Kiwi. A lot of you may know him. And he moved to France, and he's still in France at the time, but I was collaborating with him about that. And you can see that it's actually quite complicated what happens. And another thing we noticed is that when we were running this simulation, we started to include noise in the model, okay, because noise is always present, as I mentioned. And you can see that when we run several simulations with different random noise, we got slightly different results, okay? And it shows you that this light actually at every shot is slightly different. And it looks nice and continuous and smooth because you're just seeing the average, okay? But it's actually very noisy in some conditions. And so that was a bit of a problem because some application of that light, so when the light is noisy like that, we say it's incoherent. When it's not noisy, it's coherent. You can relate that to my title. And so for some application, it's not too much of a problem. And since we are talking about application, you know, why do we care about this white laser light? Well, a lot of imaging systems, they need white light, you know, to sort of color images. But sometimes, you know, normal light bulbs are not bright enough. And essentially, this is the whiteness of the sun with the brightness of a laser. So it sort of combines the best of both worlds. Okay. Now, there is another reason why this is important, and this has to do with the optical frequency comb that the dean mentioned. Okay. So what is an optical frequency comb? This is a technique that was developed by these two fellows, got the Nobel Prize for that in 2005. And an optical frequency comb is basically a series of lasers of different colors, and that are arranged in such a way that the frequencies at which the light oscillates, they are equidistant from each other, okay, along frequency. Now, you might think that this is something a bit hard to set up, but actually it's not so bad. Basically, each time you have a laser that's generating pulses periodically at regular intervals, well, the light it generates has this structure. So it's actually kind of it exists in a lot of situations. Now, what these fellows realized that they could use these frequency comb as a ruler. Okay, think about it as a ruler, and these are the tick marks of the ruler. But instead of measuring distances, you are measuring time or frequencies. And it turns out that this could be done with extraordinary precision. Okay, we are talking like 15 digits of precision. And so that was a big deal. The problem is that, you know, as with a ruler, you can only compare one thing to the other. You can only measure the difference between two frequencies. So you need to know one of the, I don't know, atomic line you're measuring to measure another one. And that changed when it became possible to generate the spectrum wide enough that you would have a frequency and its second harmonic in the same span of color. Okay? Because then when you measure the difference between 2f and f, as this complicated equation shows you at the top there, you're measuring f itself. And it offered a way to measure the frequency of light directly in absolute manner without any reference. And again, you can do that with extraordinary precision. And it opened the way to all sort of a high precision measurement, you know, for atomic clocks, for ranging, for high precision spectroscopy, detection of extrasolar planets, test of fundamental physics, and so on and so forth. So very important application, and the super continuum process is what allows you to get this broad band of color. Okay, so that was a big deal at the time. And so because of that, okay, we put a lot of effort, and we with John and another colleague from Finland, Guri Genti, we ended up writing this 50-page long review paper on the topic, and that made us famous because it attracted like 5,000 citations. And by the way, at the time when you were doing this sort of paper, you could buy reprints from the publisher. Rather than downloading a PDF. And these are the original reprints. They are gathering dust in my office, so if some of you want one or even a signed one, feel free to grab one. Feel free to grab one at the end, okay? This is from 2006, okay? 20 years in my office gathering dust. This is the mock-up that John did for that paper, okay? Now, this paper was a bit of a horrendous work, I must say, okay? It took us a lot of sweat and tear. And it was made a little bit complicated by the fact that all three of us, me, John, and Gary, in 2006, we happened to have a baby, all in that same year. So obviously that put some strain on the work, but okay, we eventually got there. Now, I have to make a little bit of an interruption here. It's a good practice when you give a lecture to avoid people falling asleep, to at some point, make a bit of a digression and talk about something else. So welcome to the middle of the lecture, to quote a famous movie. And so we're going to change gear a little bit for a few minutes. And so I just would like you to look at these two graphs. They are very nice graphs. They both look reasonably similar. But there's one big problem, or a major flaw with one of these graphs. And I'm sure that you can probably realize that. And this is what happens, okay? You can see here we have minus 0.5. And here we have something that it's not quite minus 0.5, okay? So let's look at that in a bit more detail. See, I've enlarged things a little bit. And you can see here the minus sign, it's virtually aligned with the plus sign. It's centered on the digits. It's as wide as a plus. And none of that applies to the hyphen, okay? So don't use an hyphen for a plus sign, for a minus sign, okay? This is the key message of this lecture, I think. And this is even more clear on this diagram, where you can see that the left version is aesthetically more pleasing than the right one, definitely, okay? Especially in tiny font, you could easily miss this thing there and think it's a 10 plus 2, right? And then you get orders of magnitude wrong. So how do you get this minus sign? It's not immediately available from your keyboard. But basically, the secret lies in Unicode. And I'll let you go on Wikipedia to figure out how to type it on your keyboard. But it's available on your phone, on your computer, being a Mac or a PC. And on top of the minus sign, you have zillions of other characters you can access. But for today, just remember that code, 2212. That's the Unicode for the minus sign. Okay. Now, it took some time for me to see the light, I must confess, And if you look at my record, this is my first publication in the prestigious Physical Review Letters, and it's just wrong, okay? And this is my 2006 publication with 5,000 citations, and look at that. And in fact, in that publication, some of them are right, some of them are wrong, but basically we didn't know what we were doing. It was all random. And maybe that's why it attracted 5,000 citations. But from about 10,010 onwards, I became more consistent, okay? So don't be like me, just do your minus sign properly. So we'll move back to a story. I was in my postdoc. In 2001, I went back to Belgium and came back to New Zealand a couple of years later with Fred, that we can see here. And I had actually met Fred before my postdoc, but we properly met, let's put it like that. And as Eugene mentioned, they were actually the first time Fred saw me, I didn't notice her at all, okay? Like, she was doing physics, and a lecturer was my co-supervisor, and he took the class to a lab visit, and they asked me to set up a demo, a bit like that one. I'm going to switch that off for a moment before we blew up the laser, by the way. Anyway, they asked me to set up a demo, and this group came along, and I was very stressed, and I didn't pay attention to anybody, but Fred remembers seeing me, and I don't remember at all. But anyway, we finally came together. Anyway, we came to New Zealand, and why New Zealand? Well, we wanted to learn English, and at the time, in the US, there was George Bush, and with the benefit of hindsight, George Bush was not so bad, but in Australia, there was John Howard, which didn't look very, didn't look very good as well. So New Zealand it was, and we came for like 5 years, and then life got in the way, and there were more of us. And we got stuck here, and now these guys are going through university, and they don't want to leave anymore, so we'll probably be here for a few more years. And these guys in the audience, and they're a little bit older, but I'm sure they can recognize themselves, or you can recognize them. Anyway, so I went to New Zealand in 2003 with Fred. I got this lecturer position, and for a time I kept working on supercontinuum generation. But then at some point I don't know if I got bored, or I got tired of it, or maybe I got a burnout after writing the review paper. Anyway, in 2009, I went back to the study of optical fiber rings. Okay, and here we go. Remember the zebra here with the stripe and the modulation emerging spontaneously? And we ask ourselves the question, can we get a zebra with a single stripe? Okay, like the green trace here. And you may say that, hold on a second, you just say that when you have continuous light, it would spontaneously modulate itself. Yeah, that's true, but we also have this behavior that this optical fibering, they have this memory effect, okay? And you can actually be in this, for the same condition, you can be in a low power state or in a high power state. And the high power state gets you this modulation, but the low power state is stable. So this is actually possible. Now you might ask yourself, does that have a special name? Yes, it's called a donkey, okay? you can see here, single stripe on the back of the donkey, okay? So in scientific term, we call that a cavity soliton. And these pulse turn have to be very important properties, which I'm going to mention a little bit. And this is a measurement of one of these. This is, again, it's at the scale of millionth of a second. So it's a pretty neat measurement. So what's actually happening, this soliton, basically, as we call it, is essentially a short burst of light, very intense burst of light surrounded by a low-intensity background that's going around this optical fibering. Okay? And it essentially stays there forever. It doesn't go away. Now you might think that, you know, some of the power is going to be lost, you know, and some of it gets out, some of it gets absorbed. But this soliton is so special, it has this sort of self-organized nature that it's able to draw the power it needs from the background to basically stay alive, okay? When I made these observations, I actually made them in Brussels. I went for a sabbatical in Brussels. It was my first sabbatical. And I worked with François Léaud, who was a PhD student at the time. And his PhD supervisor, you know, he was a professor and he was very busy, didn't have the time to supervise him, and so I sort of took over a little bit, and we got these great results. And this is something that's very common in nature, and I can show you some other examples of these sort of objects, which are more broadly called localized distributive structure. This was introduced in chemistry by this fellow, Ilya Prigogine, who got another Nobel Prize winner from ULB, actually. And so you can see them in vegetation, in sands, in water, and so on. Even the Jupiter Great Red Spot, you could claim that this is such a structure. Now, there's something interesting about Ilya Prigogine is that he actually was a physics teacher at ULB when my grandmother went through physics, and so she had him as a teacher. And that was during Second World War, and during the Second World War, the Germans who had invaded Belgium, they locked up the university, they locked up the non-Catholic university, they let the Catholic university open. Anyway, my grandmother couldn't attend the lecture, and so Prigogine actually was giving his lecture at home. And after each lecture, he was playing piano, and when he got the Nobel Prize, my grandmother wrote to him and get back in touch with him to remember him of these things, and he sort of, they had a good chat about it, so nice story, I think. Anyway, with these solitons, so I came back to Auckland and we started working on it, on these solitons in Auckland with two colleagues I really need to mention here. This is Stuart Murdoch and Miro Quintalo. You know, without them, I wouldn't be here today, really. So Stuart is in charge of the lab and he makes sure that the lab always works and supervises all the lab work. And Miro is also very special. You know, I actually hired him as a postdoc in 2012. And this is probably the best thing I've ever done. Since then, he has basically written all my paper. I don't have to do anything anymore. And he's now pretty much the HOD. He's acting HOD, but I think everybody will vote for him if we have to vote. And so we did a lot of things with these solitons. We showed that we could turn them on and off and move them around, and they exhibit these chaotic behaviors and whatnot. And a lot of this work also involves many students, and I'm just showing a few here that I had the pictures. There was Jay Jiang was the first PhD student working on that, and that photo is actually taken in Brussels. This is the Atomium in Brussels, the famous balls of steel. There's Yadong, and this is mine. I think he might be in the audience. I think I've seen him earlier. Here we go. And there was quite a few others. And at the time, we also started to collaborate with this fellow here, Gianluca Oppo, an amazing Italian guy, very funny, who works in Scotland, and he really helped us to put a result into perspective and to get them published and disseminated. So a lot of thanks to these people. Now, there's another thing that happens. So we are sort of now in 2010, 2012, and something happened a few years before from other groups. You know, this is in 2007. Some people in Garching in Germany from the group of Professor Kippenberg, playing with this microscopic little disc there and shining light into them, they observe this kind of spectrum coming out. Okay, and you can recognize now that this is an optical frequency cone. And that caused a lot of stir because before that, optical frequency cone, you need a lot of gear to generate it. It's very complicated, very expensive. And so this sort of showed you that potentially you could generate this frequency cone with so many important applications, but on a microscopic platform, potentially integrated like microelectronics, right? Now, if you think about what I've been telling you, you know, my optical fiber rings, light going through, generating these side bands during my PhD thesis, and so on. You can see some parallels there, okay? And so when I saw these results, I thought, haha, this is the same thing, you know, and this must be the deepest thought I must ever have, actually. And so just to put things into context, you know, in 2009, I was working on this solitaire with François Léo in Brussels, and then a colleague from France, Thibaut Sylvestre, sort of put me into contact with Professor Kippenberg and said, oh, what about you go and visit this guy and talk? And so I went there and we talked, and I told him, yeah, there must be some solitons in there, what do you think, and so on. And that, and indeed there was, you know, and they observed that a few years later, and from there on, you know, all the theory we had known for the optical fiber ring and the thing I've been talking about could immediately be applied to that field, okay? And you have to realize that before that time, these two worlds were totally separated. You know, we didn't know each other, we didn't read each other's publication. Another thing that happened is that we had very powerful numerical models for my system, and that they didn't know about, and their simulation took ours, and when we started to apply our techniques to their system, we sped up their simulation by literally a factor of thousands or 10,000. So it really made a big impact on that field. And I would like to insist this is pure luck, you know. I was basically there at the right time, and to say that, to observe that this is the same thing as you can do now, right? So what's actually happening, if you think about it, once we have a soliton in these rings and it goes round, at each round trip, a little bit of the light comes out. And so you get this periodic burst of light coming out. And as I mentioned before, periodic burst of light is associated with the discrete spectrum, and it explains why we have these optical frequency come from this sort of microscopic platform, okay? Now, we can't really fabricate these things in New Zealand, but there's a lot of groups now around the world, and even industrial partner work on these things to integrate that. There's a big efforts toward what we call integrated photonics. Photonics is the science of light. So in the same way you have integrated electronics, we are moving toward integrated photonics. And you can see some of the realization here. Again, look at the scale. These are these rings integrated on sort of the same sort of platform you can build with an electronic fabrication facility. You can see wafers here. You can see one of these tiny rings being sort of illuminated with the light going around. And this setup here is an example of the generation of an optical frequency comb powered by a AAA battery. And this chip you see here, this is a 200 micron rings there. It's in this little red square there. Okay, so you can really see that this is moving towards industrial product, mass produced, and maybe it's going to end up on your phone one day. Okay. Another interesting thing I like to show that was shown a few years back. This is a prototype of an integrated optical atomic clock. This is more accurate than an atomic clock. That's the potential to be 1,000 times better than an atomic clock. And it's all based on these rings, which is a millimeter to micron size, and on a gas cell, which is smaller than a coffee bean, okay? And so it really shows you that, and in these two rings, we have these solitons going around that are sort of part of the process to get the clock reading. So this is moving quite fast towards some real applications, like integrated and mass-produced applications. So just would like to, in the last couple of minutes, I would like to talk about our last topic, which is about spontaneous symmetry breaking. And here I need to start by that picture. Okay, you can see me with sunglasses. And I don't know if they are polarized sunglasses, but you're probably familiar with polarized sunglasses. And you know, they give you a bluer sky when you look at the sky. And polarization is to do that, you know, when you have a light beam, the electric field oscillates. And it can oscillate like that, or it can oscillate like that. Okay, you basically have two components. Okay, and what polarized sunglasses do is that they select one of these components. But optical fiber, they support both components. And what I've drawn here is it's not two rings on top of each other. These represent the two polarization components that can propagate into my ring, but you have to realize that this is propagating the same fiber. Okay. Now, so we can shine the light into both these components, and you might think that if I shine the same amount of light in these two components, well, I'll get the same amount of light at the output into these two components. But again, nature is more complicated. And it so happens that you can, what we call, break the symmetry. And this is a bit like, you know, when you have a pencil on its sharp part, you know, and you hold it vertically, perfectly vertical, and you let it go, it's going to fall in a certain direction, but it may fall left or it may fall right. And, you know, essentially you start from a situation which is symmetrical, you end up with a situation where the symmetry is broken, so hence the symmetry breaking. And we can do that with light. Now, again, nature is a little bit more complicated than that, because as I said, you need to excite these two components in exactly the same condition. And of course, there's always some imperfection. Nature makes it hard. And we managed to do that, but it took a little bit of effort, as you're going to see in a second. And again, we can do a parallel with animals. These are real animals. You can see this crab, which is this claw, which is massively larger than the other. And this is a New Zealand bird. And all these birds have their beak bent in the same direction. Like they all go through this symmetry breaking in the same way. So quite interesting. Apparently, it helps them open oysters. Okay, better than if the beak was straight. So that's the setup we developed with postdoc Bruno Garbin from France to do that. And I'm not going to comment on it, but you can see that it's quite complicated to control. Okay, it took us a lot of effort. It was like climbing a mountain, but we got there. And we got these beautiful experimental results. And then we tried to publish them. We sent them to a first journal. We get rejected. Second journal rejected. Third journal rejected. And each time we had these comments that were purely theoretical. They didn't care at all about the experiment, okay, which was essentially 95% of the publication. Okay. And at the end, just before it was about to be accepted, we got this final comment, and the reviewer asked us, "Oh, you really should add a 3D plot to clarify things, And so we did this 3D plot to clarify things as they request, and I hope you can appreciate how it clarifies things. Oh, hold on a second. There's something wrong with this picture. I hope you can see it, the minus sign is not right. So let's check the next slide. Here we go. Much better now. Yeah, now it should be clear what's going on, right? So here we go. We made these 3D plots, and I remember when my next PhD student came along, and he read this paper, and he got to this picture, and then he asked me, "Why do you put this picture? It really doesn't add anything." That was Liam, by the way. Anyway, as we were playing with the experiment, one day we bumped into this. Again, this was perfectly luck. We bumped into this recipe for perfect symmetry, and all of a sudden our experiment was so much easier. Okay? And we didn't have to do anything with that. And that happened during the period where this Dr. Julien Fatome came to join us. That was just before COVID. He came in 2020, and he got stuck here, and he stayed for 2 years. So that was really good for us. We also had another postdoc gang. And if you look at this picture, he's from China. He was from China. He went back to China after this postdoc. And if you look at this picture, you can notice that both he and I, we both have the same head, which I brought here. And the reason this head is so famous is because Gang told me that in China, I'm kind of famous for all these works on the optical fiber rings. And so there's a lot of Chinese people, basically they call me the Lord of the Rings for that reason. And so when Gang was about to leave, Julien bought the same hat as mine, so he can bring it to China saying, "This is the hat of the Lord of the Rings." Okay. So that's the story behind the hat. So what actually happened for the perfect symmetry is that because of the nonlinearity and other complicated phenomenon, it may happen that the optical fiber ring adopts this sort of geometry there. And you can see that the two sort of components, as I call them, they are not connected. Essentially what happened is that the two polarization components, they swap at each pass in the ring. And the result is that over many swaps, both components essentially undergo the same behavior, exactly the same physics. All the difference are essentially averaged out, and they become perfectly symmetrical, and this is why we can realize then this symmetry breaking in perfect condition. And you can see that in this picture by noting that, the light goes on and off and on and off and on and off. This is the swapping that we're seeing about. And we could also argue that this is like a mix of a donkey and a zebra kind of thing. Anyway, you might wonder, okay, why is that useful? I think I'd like to stress that there are some useful applications for that. And Liam, who's the last PhD student I had who finished recently, studied some of that. And the first thing is that remember the pencil, we can fall left or right. Well, imagine lots of pencils that fall left or right. You can use that as a sort of random number generation. And the thing is that what's magic here is that these numbers are truly random. Okay, if you use a computer to generate random number, at some point they repeat. They're what we call pseudo-random. Okay, but these are truly random, and Liam was able to show that they were just perfectly ideal random. And this has some application, for finance and other sort of mundane application like that. Some people in the finance world, they really want numbers that are random and that absolutely cannot be predicted. Now, the other thing we can do, and we're still working on that, if you have lots of these pencils and you sort of connect them in a certain way, they can actually represent a combinatorial optimization problem. Okay, and one of them, for example, is the sort of traveling salesman problem, finding the best route towards a set of cities to spend the less of time and so on. And there is a lot of problems like that in everyday life, for logistic, optimization of factories, optimization of networks, and so on and so forth. And these problems become very complicated very quickly, okay? And once you have a sufficiently large number of pencils, it becomes intractable with the normal computers. And we can actually set up our optical system such that it actually naturally goes towards the solution of these problems, okay? And this is what we call a Ising machine, and this is what we are now working on, okay? Anyway, this concludes my talk. Just before finishing, I'd like to thank funders. Okay, this research comes with it costs some money, and there's a number of funders who have helped me along the way, along the years, and only a few of them are shown here. And finally, I'd like to thank you for attending the talk and for listening. Thank you.